Okay, so we were on number 4 on page 390, and it was saying that an electronic fish finder uses sound pulses to locate schools of fish by echolation. What would be the time delay between the emission of a sound pulse and the reception of its echo if the school of fish was located at a depth of 35 meters in a lake? So it's asking for the total time, the time it takes for the sound to go down, hit the fish, and come back. Okay? What they give us in the question is just delta D one way, so we're going to need to double it. The distance that the sound pulse has to travel is 70 meters. Okay? And it says assume the temperature of the lake is 20 degrees. And some of you would have probably tried to use 331 plus 0.59 meters per second degrees Celsius times this 20 degrees because you saw a temperature and that equation has a temperature in it. But that equation is for the speed of sound in air. Last time I checked, the little fishies don't live in air. Okay? They are in a lake. So you have to go to page 387, and there's a chart there, and you'll notice that for liquids, it has in brackets, it's the middle of the chart, has in brackets 20 degrees. So this is the temperature of the speed of sound in a liquid at 20 degrees. Lakes are fresh water, so when you look it up, you see the speed is 1482. Okay, so our speed is 1482 meters per second. And now we can find our time. V is equal to delta D over delta T. So delta T is equal to delta D over V. And we're looking for T total, so we need to use D total. So 70 meters times 1482 meters per second. This is going to be tiny. Just in case you were thinking you were screwing it up, no, you are not. It's 0.0472 seconds. Okay? Now this should make sense though. It's traveling 1,400 meters per second and it's only going 70 meters. And it means that they send it down, they find the school of fish, they can get some of those fish before the fish swim away. So you don't want it to be taken a couple of minutes because if it does, the fish will be gone by then. Number 5. You want to estimate the length of a large sports complex. You generate a loud noise at one end of the stadium and hear an echo 1.2 seconds later. Okay, so you're over here. Whatever you do, you generate a loud noise. The sound wave travels down, travels back. Delta T total is 1.2 seconds. The air temperature is approximately 12 degrees. So this time you really can use 331 meters per second plus 0.59 meters per second degrees Celsius times the 12 degrees because you're in a gymnasium, not a swimming pool. Okay, so when you do this one, you get 338.08 meters per second. All right, if we keep reading, it says how far away is the far end. You're just looking for delta D one way. So VAV is equal to delta D over delta T. So delta D is equal to VAV times delta T. So the VAV is the 338.08 meters per second. Now, so our full time is 1.2 seconds. Somewhere you have to divide by 2. So you can either divide by 2 and only fill in the 0.06, or you can divide the whole thing by 2 once you've filled in the 1.2. And when you do this, before you divide by 2, you get 405.696 meters. Divided by 2, you get a delta D of 202.848 meters. That is the length of the gymnasium. Number 6. Be good if I could count. How long will it take for sound to travel 2 kilometers in air at a temperature of 22 degrees? So my delta D is 2 kilometers or 2,000 meters. And it tells me my temperature is 22 degrees. So V is equal to 331 meters per second, 0.59 meters per second degrees Celsius times 22 degrees Celsius. So my speed is 343.98 meters per second. Okay, so I have my speed and I have my distance, and it wants to know in part A how long is it going to take to travel, the sound to travel. So V equals delta D over delta T, so delta T is equal to delta D over V. So 2,000 meters divided by 343.98 meters per second. And we will get a time of 5.814 seconds. Okay, and I'll come back and talk about that when we finish the question. The speed of light is 3 times 10 to the 8th meters per second. How long does it take for light to travel 2 kilometers? So for light, again, we're going to do V is equal to delta D over delta T. So delta T is equal to delta D over the V. 2,000 meters over 3 times 10 to the 8th meters per second. This was sound. So the delta T of light is going to be significantly tinier. It is going to be 6.6 repeating times 10 to the negative 6 seconds. 6 nanoseconds. This is so tiny that we basically say that light can get there instantly. Now this becomes important. Notice that it takes sound roughly 3 seconds to travel 1,000 meters, 3 seconds per kilometer. Okay, not quite, and obviously it depends a bit on the temperature, but an estimate is 3 seconds per kilometer. Why is this important? Well, it's important, it's cool when you're watching a thunder and lightning storm. If you've ever been watching a thunder and lightning storm, you can count between when you hear the thunder and when you see the lightning, and it'll give you a rough idea of how far away the storm is, right? So, and you have to count slow, like 1, 1,000, 2, 1,000, 3, 1,000, or 1 steamboat, 2 steamboats, 3 steamboats, or 1 Mississippi, 2 Mississippi. Something that will make sure that there's a second between each counting. So you hear the thunder and you count, and maybe you get to 9. If you get to 9 seconds before you see the lightning, the other way around, excuse me, you see the lightning and then you count, and maybe you get to 9 seconds before you hear the thunder. And if you do, it means the storm is about 3 kilometers away, because it's roughly, right? This was 2 kilometers and it was almost 6 seconds. So it's a decent estimate if you're, if it's the summertime and you're in your backyard and you want to impress your friends, or if you just want to know how long before you get drenched. Every 3 seconds is roughly 1,000 meters, okay? But the coolest part is then when you see the next flash of lightning, count again. Because then if you only get to 7 seconds before you hear the thunder, it means the storm's getting closer to you. And then it'll be 5, and then it'll be 3, and then all of a sudden you'll see the lightning and the thunder will happen instantly, and you'll almost scream. It'll be so close and so loud. But then if you wait, the next one will be further again. So it's like the storm moves in to where you are, and as it does, these two get closer together, and then the storm moves out. Whoops, there's the part C. The rumble of thunder is 8 seconds after the flash of lightning. How far away? So for part C, you just have to do delta D is equal to V delta T. It's 22 degrees, so 343.98 meters per second times 8 seconds, and you get a delta D of 2,751.84 meters. Okay, we assume the lightning is instantaneous. Okay, so it is kind of cool. And the reason is because, like, if you are racing a fast person and the race is just across the hall, they don't have a lot of time to build up a lead, so you'll get there almost at the same time. But if you're racing down to the Dairy Queen, they have a lot of time to build up a lead, and they're going to be much further ahead of you by the time they get there. Same thing happens. Short distance